All right, next section deals with Friedel-Crafts Isolation. So far, we've looked at halogenation, sulfonation, nitration, alkylation, and now we're going to turn our attention to acylation. You need to know the difference between acylation and alkylation, right? Alkylation just means you're adding an alkyl group like methyl, ethyl, butyl, sec-butyl, so on and so forth. Whereas an acyl group is where we have a carbonyl in between our aromatic ring and our R group. So we call that an acyl group. All right. So if we have an acyl group, we need to do an acylation. So if we start with an acid chloride, and you should remember this functional group, this is not a carboxylic acid, this is an acid chloride here, and aluminum trichloride as our Lewis acid, you can imagine that one of the lone pairs on the chlorine can dump electron density into the aluminum. Well, what's that going to look like? What will that electrophile look like that's going to allow this acylation reaction to occur? Let's take a look. So we end up producing an electrophile that we call an Acilium ion, and you need to know what an Acilium ion is. So first curved arrow, we dump the electron density in there, and then we break this bond, then we end up with this Acilium ion. Notice that the Acilium ion that's drawn in the green box, right, the carbon has an incomplete octet, but there's another resonance contributor to the overall resonance hybrid, which is going to be even a greater contributor, and that is this one here, where the carbon does have a complete octet. So again, this will contribute more to the overall resonance hybrid because everything has a complete octet. Well, there we go. There's our Acilium, and there's the resonance structures. So what's the reaction look like, the acylation mechanism? What do you think? First step, nucleophilic attack. Second step, the formation of the sigma, or after the nucleophilic attack, rather, you form the sigma complex, and then there's a proton transfer at the end in order to install the acyl group, which is over here on the far right. Remember, the reason why the proton transfer occurs is that we restore aromaticity, right? We regenerate our aromatic ring, and that is one of the driving forces for the reaction. Now, there's some interesting nuances to Friedel-Crafts acylation, and one of the coolest nuances is this one here. Remember, I showed you just a few minutes ago that it's difficult to install a primary alkyl group or an alkyl group attached from a primary, to attach the carbon that was attached to a halogen on a primary alkyl halide. It's difficult to do that. And so the Friedel-Crafts acylation allows us or provides us a route to add a straight chain to our aromatic ring. How would you do that? Well, you just determine the number of carbons that you want to add. So here we want to add an N-butyl group, 1, 2, 3, 4 carbons. And so what we do is we start it with the acid chloride that has 4 carbons. So we have 1, 2, 3, 4 carbons here. We do our Friedel-Crafts acylation reaction, nucleophilic attack. We form the sigma complex, we do the proton transfer, and we end up with this compound. Well, I'm going to teach you a brand new reaction, and it's called the Clemensin reduction. Okay, right here, the Clemensin reduction. And what the Clemensin reduction does is it removes the oxygen from the carbonyl, and it replaces these 2 bonds to 2 bonds to hydrogen in order to make an sp3 hybridized methylene, CH2. All right. And so the way that you do that is you treat it with zinc and mercury. And you notice that the mercury is in these brackets here. That means that it's what's called an amalgam, which means that the surface of the zinc is coated in mercury. And then you treat that with hydrochloric acid and heat. This is another mechanism that is not included in our textbook. It is beyond the scope of our course. So it's going to be one of those reactions that you simply have to memorize, the Clemensin reduction. So what are some nuances of the Friedel-Crafts acylation? Well, the one nuance that you have to have memorized for the Friedel-Crafts acylation is that once we install one acyl group, okay, once you have one, you're not going to get polyacylation. It's not going to happen. Okay, polyalkylation was something that we saw, but polyacylation won't happen. Why? Because the acyl group serves to deactivate the ring toward further acylation. And that covers everything that you need to know about Friedel-Crafts acylation. With that in mind, let's take a look at a problem where we have to apply our knowledge of Friedel-Crafts acylation. It says identify whether each of the following compounds can be made using direct Friedel-Crafts acylation, or whether you have to do, direct Friedel-Crafts alkylation, or whether you have to do an acylation followed by a Clemensin reduction. Well, what I like to do for these ones is solve them using retrosynthesis, right? If we start with A, okay, if we think about this going backwards, all right, we would need to have our aromatic ring, okay? And what would have to be our electrophile? Well, if we're adding these 5 carbons, and it's attaching at this carbon, that means that we would have to have the 5 carbons, and we'd have to have the positive charge on here. That's a primary carbocation, right? Which would come from a primary alkyl halide, like this, okay? And we know that we cannot do that. We know that that's going to cause a rearrangement to occur, and therefore we would have to do a Friedel-Crafts acylation first, right? First, we'd have to take the aromatic ring, okay, and I'm still talking about A here. We'd have to treat it with the acid chloride so that we don't get any rearrangements or anything, and aluminum chloride. That would give us this compound. So we have our carbonyl here, so we make the ketone. And then in the last step, we would treat it with, and I'm kind of running out of space here, so let me see. Let me just move the whole thing over here. Okay, then you would have to take it and you would treat it with zinc and mercury, our amalgam. You would treat it with HCl. Okay, and you would heat that up a little bit for Clemensin reduction. And that would remove the oxygen and replace it with 2 hydrogens, and you'd end up with a desired product like that. So this is the solution to A.